Thank you very much, Manoli. Thank you, everybody. This is work primarily by my postdoc, Joel Dalin, and then, of course, Rick DeVore, who developed the numerical code, whose results I'm going to be showing you. And we're trying to understand what is the nature of three-dimensional reconnection in solar flares. So let me show you why it's important. Oops, let's go back one. So what is solar flare? Here's a classic example of an eruptive flare. Flares are the most energetic phenomena in the solar system. They have tremendous relevance to high energy cosmic activity of all types, both in other stars and also in more exotic objects. They have extremely important space weather impact. They drive the most energetic particles, survey ionosphere, etc. An eruptive flare consists of both an intense heating, what you see down here. This is the flare loops that are visible down near the solar surface, and these loops contain plasma of order 20, 30 million degrees. Up above, you see this long elongated structure, which we believe is a current sheet where reconnection is taking place, creating these loops, and also launching this big fat plasmoid, which turns into a coronal mass ejection. And this particular one travels out at 4,000 kilometers per second. So flares are giant magnetic explosions. The open questions are, one, how do flares release so much energy in such a little time? In other words, they're enormous power, up to 10 to 11 ergs per centimeter squared per second. Basically, a strong flare can give you a luminosity comparable to the solar white light luminosity. That's why you can see a white light flare. So how can they be such efficient energy releasers, and how do they accelerate so many electrons in the corona? For a powerful flare such as this one, you can get up to 50% or more of the energy being released in the form of high energy electrons. And that requires accelerating most of the electrons in the corona. By far the most efficient particle accelerators in nature. To address these questions, we use high resolution 3D MHD simulations. We know that the answer to these two questions must be due to the magnetic reconnection that powers the flare. So here's a cartoon of flares by Gordon Holman. This cartoon is not really the best one could do, but anyway, it's good enough. What it shows is down here are the flare loops. This is where the 20, 30 million degree plasma is, corresponds to this. Up above here, you have a current sheet. Now, unfortunately, Gordon doesn't show this. He just shows us an X point, reconnection, flows coming in and flows going out. But in fact, you actually get a current sheet. You don't get just a simple little X point. And then up above, the reconnection creates both the flare loops and also launches this plasmoid as the CME. So this is the generic picture of flares, and we know it must be correct because it looks so much like the actual observations. And also there are many other observations which fit this kind of cartoon model. Okay, so in order to understand the reconnection, to try to get constraints on the reconnection, since we can't see the corona directly and we can't see what the reconnection is taking place, what we can look at, fortunately, is its imprint on the chromosphere. So the way this works is that, suppose we have the reconnection up here. This, for example, is a 3D structure now. So there is an X line that goes from this point to this point, let's say. And like I said, this really should be a current sheet rather than the simple X, but whatever. The reconnection here will launch waves, mass motion, and particles downwards. These will impact the chromosphere and cause a brightening of the chromosphere. So in time, as the reconnection proceeds up here and more flux, outside flux gets transferred through the reconnection and into these coronal loops, as is shown by this cartoon here, where this system involves this system, what you will see is the imprint of the reconnection on the chromosphere progressing in time outwards. But also, if there's 3D structure along here, you will see that in the nature of the evolution of the ribbons. And if you look at the actual chromospheric ribbons, here's from a flare that Kostis Pontikakis will discuss right after me. What you'll see is that here's this is just one ribbon. So it corresponds to one of these lines. You can see, in fact, it's really complicated, and there's all sorts of structure. It curves around, and it has this kind of whirly structure. Okay. So this evolution and this structure is all due to the nature of the reconnection that's taking place here. So it gives us kind of the best insight as to what's happening. How could the reconnection be so efficient? One aspect of the reconnection that we know, that we think is there, is the presence of plasmoid, reconnection plasmoids. If we put this picture on its side, and we have a horizontal current sheet, we get this. This is a results of a simulation by Joel Dalin, where he's taken a kinetic model, kinetic current sheet, and just let it reconnect. And what you see is from the kinetic model, the current sheet, as a result of reconnection, breaks up into little plasmoids, little magnetic islands. Now, this simulation is very different than the actual sun because this simulation is kinetic. Its scale is of order meters, where here we have 100,000 kilometers, and also it's a very simple 1D initial system and has periodic time conditions and so on and so forth, which is not what's going on here. So it's a far cry from the real system, but it shows you that plasmoids tend to appear in reconnection. And here's some observations by Pankaj Kumar, where he seems to see plasmoids in this jet reconnection, so-called breakout jets. Now, these blobs here, Pankaj deduces their islands because they're in the right location and they have the right motion to correspond to ejection outwards from the reconnection point. But you cannot see the magnetic field directly. You can only deduce that these things are plasmoids. So it's not definitive observations. It's just kind of very suggestive, since we cannot measure the magnetic field directly. So we need to use simulations to try to understand what's going on. And here are some ultra high resolution eruptive flare model simulations done by Joel Dalin. This is a calculation that he's just completed and he's now writing up a publication. What he's done is taken a simplest model for an active region. Here's a bipolar active region kind of stretched out in order to enhance the ease of which you can do numerical resolution. It's sitting here not at the equator, so you have initial symmetry, but the symmetry is broken by the evolution. He drives this active region, so I would say, by putting shear here at the polarity inversion line, and then eventually an eruption will occur. And he puts ultra high resolution at the flare reconnection to really resolve the 3D nature of the reconnection. So he uses adaptive mesh, resolves important fine structure detail in the highest detail to date. So this is the highest resolution simulation that's ever been done of flare reconnection. The initial magnetic field is smooth, the driving smooth. So all structure that you see must be due to the dynamics of the reconnection. Here's the current density through this plane right here, this plane you see. And as the system expands outwards, poof, you start getting reconnection. And you can see the islands forming right there, as a matter of fact. Same thing here. This is the line of sight magnetic field, so the shear field through the plane. You see the shear field is ejected outwards. That's the whole point of the flare, to eject that field out. And if you compare it to the actual September 10 event, it has a similar characteristic. So this is basically what must be happening in this event as well. Now, when you look at the current sheet in detail, the flare current sheet, you see this continuous ejection of little blobs, which in fact we know are plasmoids because we can measure them. But these are 3D plasmoids because they have a finite direction in and out of the board. If we want to get the analogy to the flare ribbons, we can do that. What we do here, so what Joel has done, in order to get the analogy to the flare ribbons, he measures the length of the magnetic field lines. And then he says, when the field line shortens, so if you look at the field line here, as it goes to the reconnection region, it shortens, especially when you add in the shear in this direction. So, when the field line shortens, then it must have done so by reconnection, because when you're imposing the shear, all you're doing is you're lengthening the field lines. The field lines expand outwards and they get stretched out by the shear. Shortening the field lines must be due to the reconnection. So by measuring the shortening of the field lines and plotting that, you you're basically getting the flare ribbons. So this, you can think of this as a picture of the flare ribbons growing out from the polarity inversion line. As you can see, as it starts, you get relatively smooth ribbons, but then they kind of, you get all this structure at the edge of the ribbons. You can see that better in this movie. Let's see if I can back it up, where what he plots now is basically the leading edge of the ribbons. Where
5 minutes.
5 minutes, perfect. Okay, now if you compare this, it starts off relatively smooth because of the strong shear field, but then later on you get all these whorls, the swirls. Notice that? And interestingly, the simulations, the observations also show swirls. This is the edge of the ribbons, and this is really the edge of the ribbons as well. Of course, we don't get that huge bending and everything because our magnetic field distribution is quite simple compared to the magnetic field distribution here. But the reconnection dynamics is starting to look very similar to the reconnection dynamics that's observed on the sun. So you get a lot of fine structure, and they must be due to the reconnection dynamics, in other words, plasmoids. And to show there really is plasmoids, whoopsie daisy, what Joel has done, he has plotted the field lines from a line cutting through a plasmoid that's observed in the flare current sheet. So he's plotted all those field lines and asked where do they come down to in the chromosphere, and here's where they are. So these colors correspond to these colors down here. So these are the foot points of the field lines that start here. And you can see these plasmoids are what is forming these swirls. These swirls are due to these twisted magnetic field lines of these plasmoids. So the magnetic field lines traced from a plasmoid connect to a whorl. And indeed, if you look at the observations, you can see all these whorls forming, all these whorls in the observed chromospheric ribbons. So in summary, we had the new high-resolution MHD calculations of eruptive flare, and we've done the highest resolution to date of 3D magnetic reconnection of flare. You see many plasmoids are generated, and the energy release is fast. In fact, for this flare, for this event, we got an injection speed of order the alpha speed, around 2,000 kilometers per second. And the release was plenty fast. The flare ribbon structure reveals complex 3D dynamics. We see a lot of whorls in the ribbons, in our numerical ribbons. They're evidence of plasmoids, which are critical for particle acceleration. There's a lot of theories on how these plasmoids accelerate particles. And similar structures are seen in the high resolution observation. What's next? We need to make detailed comparison to observations, quantitative comparison. We need to incorporate particle acceleration into the MHD models. We have a theory for doing that, so-called K-arms. This is the goal of the Sulfur Drive Center, which we're involved with. But we also need high resolution hard X-ray imaging. We need the next generation mission to RESI. Fierce is one such proposal, but whatever it is, we need to advance our understanding of flares by advancing our observations with the high energy release. So hopefully we'll get something like this for the next maximum. Thank you.
Thank you very much, Spiro. Thank you for keeping in time as well. Excellent. So I see one request for question by Vasilis. Vasilis, could you please go ahead?
Yes. Hi, Spiro. Excellent talk. Thank you so much. I mean, I was interested about plasmoids for years because we were seeing this plasmoids ejected out of current sheets when you have reconnection between emerging and pre-existing magnetic fields and so on. So it's a very interesting feature of this reconnection. I just want to know, in your simulations, and since you mentioned this is 3D, right? Mm-hmm. What is the mechanism of the formation of the plasmoids? It's like due to the tearing mode instability, for example? And how does this connect with the resistivity that you have in your simulations?
Okay.
Does the formation of plasmoids depend also on the value of the resistivity that you have?
So let me do the last one first. So
Sure.
the resistivity definitely makes a huge difference. So we can think of it as the the effective Lundquist number. In these simulations, we use the numerical resistivity, so we don't put in explicit resistivity. We have done simulations with explicit resistivity, but uniform resistivity, of course. And what we find is that the results are very similar. You have to have an effective Lundquist number above 1,000 or so to get, to get that the reconnection layer is dominated by plasmoids. Otherwise, what will happen is that the current sheet doesn't grow very big. So this gets back to your first question as to what's going on here. Why is it that we're getting these plasmoids? You can think of it as tearing, but it's not really tearing because tearing occurs for initial equilibrium, right? I mean, if you think of the tearing and stability, what happens is you have an initial equilibrium in the current sheet with no cross field in any field across the current sheet, right? This current sheet, the flare current sheet, is more like the magnetotail current sheet. There's a cross tail field, and there's no kind of initial equilibrium. So the way to think about it is that what happens is that you're forming the current sheet because the field lines are trying to stretch out to minimize their energy by expanding the shear field outwards. I want to kind of get to a lower energy state by just expanding outwards. As they expand outwards, they form a current sheet just like the heliospheric current sheet is formed out by basically this expansion. So now you would say, well, okay, you have this current sheet. Why don't they pick some spot and just reconnect from there? And you'll have, you don't need islands. All you'll have is just some central spot, and away you go. The problem is that you run into the Sweet-Parker limit about, in order to have fast reconnection, you have to both process the flux, so you have to have a thin current sheet so your diffusion rate gets up high enough. But you have to diffuse the flux through there, but you also have to push the mass out of there. You got to transport the mass out of there. The mass needs a wide opening, otherwise it can't get out fast enough. So what the plasmoids do for you is they kind of widen the ends of the current sheet and let the mass come out quickly. If you try to have a current sheet that reconnects only by kind of like a Sweet-Parker reconnection, it just cannot get the mass out fast enough, and the reconnection will be too slow to explain something like a flare. You won't be able to get a 1/10 the outlet speed. So it's a really important issue. It's a really important question, but it seems to be generic that the plasmoids are what allow the reconnection to go fast by widening the current sheet. The interesting thing, Vasily, is that if you look at the September 10th flare, we don't see this widening.
Yeah.
We see it in the observation, and we see it in the simulations, but for some reason we don't see it in that particular flares. Kind of real mystery there.
Spiros Patourakos has raised his hand. So Spiro, could you make it quick, please?
Yes, thank you. Γεια σου, Σπύρο.
That's what.
Πολύ ωραία, πολύ ωραία. I have a short question. So, how big are typically the simulated plasmoids? Could we hope to retrieve them with either an UV imager or a white light? No?
Yeah, definitely. I mean, if you saw the observations by Pankaj Kumar, those plasmoids were of order, a few thousand kilometers in size.
No, I mean the simulation. The simulated plasmoids, how big are they?
They're too big. In the simulation, they're of order tens of thousands of kilometers. If we go back to the,
Okay.
No, they would be easily seen. The problem is, what is the temperature, right? What is the temperature of the plasma in the plasmoid and how dense it is? Right.
Okay, thank you.
They have to get big in order to keep the reconnection fast.